Hi everyone. This is the session on data structures and algorithm for PGD AI. Last session on graph. Previously we had covered the heap and the priority queue, and Jaime Dosawa has been persistent and consistently managing the as a lead this AIML study circle with data structures and algorithm sessions for past 7 or more sessions with sections within it. So we want to conclude the data structure session with his tremendous effort and excellent presentations. And you're all most welcome to follow that and be able to use it for your advancement in either for the exam or for the career. With that, uh, Prakash is signing off and giving the handle to Jamit Dosawa. Jamit, go ahead, take it over and complete the last session on graph. Thank you very much.
Thank you, Prakash, sir, for that. So, hello everyone. Welcome to the Data Structures and Algorithms session 7.1, which will be focusing on graphs. So let's get started with graphs. So what are graphs and how Wikipedia's definition describes it? So a graph is an abstract data type that is meant to implement the undirected and directed graphs concept from the field of graph theory within the mathematics. And the graph data structure consists of vertices and edges, and also the unordered pairs of these vertices from undirected graph, or a set of ordered pairs for directed graphs. These pairs are known as edges, and for a directed graph are also known as edges, but also sometimes arrows or arcs. So arrows or arcs are basically used in directed graphs to show, in a way you can simplify it to say that to show an arrow towards the vertex, from one vertex to another. So graphs are flexible data structures used to model problems defined in terms of relationships or connections between objects. Objects are vertices, and relation between these objects are represented by the edges between these vertices. So how do we use graphs? So, or what are the methods to use it? So this is what the search methods are used for. So search methods are techniques for visiting the vertices of a graph in a specific order. Generally, either breadth first or depth first searches are used. Many graph algorithms are based on these basic methods of systematically exploring a graph's vertices. So now applications of graphs. First are graph algorithms that solve problems modeled by graphs. Many graph algorithms solve problems related to connectivity and routing optimization for computing minimum spanning trees, finding shortest paths, and solving the traveling salesman's problem. Traveling salesman problem is nothing but traversing the vertices and finding the shortest path from where we started. The counting network hops, counting the smallest number of nodes that must be traversed from one node to reach other nodes in an internet. So this information is useful in internets, which the most significant costs are directly related to the number of nodes traversed. Then topology sorting is a linear ordering of vertices in a directed acyclic graph, so that all edges from left to right. Acyclic graph is nothing but where from the vertex that we started traversing and we cannot get back to it is called an acyclic graph. So one of, in a short manner, so one of the most common uses of topology sorting is in determining an acceptable order in which to carry out a number of tasks that depends on one another. Then Another is graph coloring. Graph coloring, a process in which we try to color the vertices of a graph with different colors, and we try to determine the minimum number of colors required to meet these criteria. So, which is called the graph's chromatic number. Moving with the further applications of graph, we have Hamiltonian cycle problems. So problems in which one works with Hamiltonian circles, paths that pass through every vertex in a graph exactly once before returning to the original vertex. So remember the traveling salesman problem. This that is a part of a Hamiltonian cycle problem. So in as mentioned before, uh, traveling salesman problem, we look for the Hamiltonian cycle with the minimum cost. The clique problems, where problems in which one works with regions of a graph where every vertex is connected somehow to every other. Regions with this property are called cliques, and some clique problems focus on determining the largest cliques that a graph contains. Other clique problems focus on determining whether a graph contains a clique or of a certain size at all. Then there is a conflict serializability. serializability. So, complex serializability is nothing but a concept in a database that ensures that transactions that are happening can be executed concurrently without causing conflicts. So, in simple terms, it means that arranging transactions in a way that produce the same result as if they were uh, executed one after another. And if the graph doesn't have cycles, indicating that no conflicting dependencies, the schedule is a conflict resizable. So now with the description of graphs, so so graphs are, as also mentioned first, the graphs contain objects, and there are they are represented with graphs are used to uh, model problems. So there are objects and there are a relation between these objects. So the objects are vertices, and the relation between them are represented by the edges between these vertices. So graphs are composed of two elements, vertices and edges. So vertices represents objects as said, and edges are the relationships. So you can see the representation of a graph uh, which contains vertices and edges. A graph G equals to V and E, where V is the set of vertices and E is the set of binary relation on V. So for figure A, you can see that for vertices 1, 2, 3, 4, we have the relations uh, as it's a directed graph. You can see the arrows moving towards and from vertices. So these are the relationships. As one has the arrows going or relations going towards 1, 2, 4, and 3. You can see uh, their pairs in the set of E for figure A. Similar is for 2, as 2 is going towards 3 and 4, and 3 is going towards 2 and 4. Now now in a directed graph, uh, yeah, for a directed graph it's done, but for an undirected graph, you can see that every pair is mentioned once. So you have uh, the set for V, which are vertices, and you have the set for E, which contains pairs. Now these pairs will occur once. So 1 and 2 is equals to 2 and 1. So in the, keeping that in mind, all of the ordered pairs are, or all the pairs are added into the set of E. So there are two concepts relating to graphs, which are adjacency and incidence. So let's first start with adjacency in a directed graph. So in a directed graph, the adjacency between two vertices A and B means that there is a direct edge from vertex A to B. So in a directed graph GV, G, V, and ordered pair VE, if there is an edge U, V belonging to E from vertex U to vertex V, then the vertex V is said to be adjacent to vertex U. That Then for adjacency in an undirected graph, the adjacency between the vertex A and B means that there is an undirected edge between vertex A and vertex B. This implies that the connection is bidirectional. So formally, an undirected graph G equals to VE, where UV belongs to E between vertices U and V. Then vertex U and vertex V are said to be adjacent to each other. In the example, you can see for image A, the vertex 2 is adjacent to vertex 1, but vertex it's a directed graph. So vertex 2 is adjacent to vertex 1, but vertex 1 is not adjacent to vertex 2. On the other hand, vertex 2 and 3 are adjacent to each other, and a graph in which every vertex is adjacent to each other is called complete. Moving forward with the incidence. In a directed graph, the edge UV is incident from or leaves vertex U and is incident to or enters vertex V. So in the image, you can see that edge, there is an edge 1, 2 is incident from vertex 1 to vertex 2. So that is called that is how incidence is formed. So in a directed graph, the in degree of a vertex is the number of edges incident to it, and out degree is the number of edges incident from it. In an undirected graph, the edge UV is incident on vertices U and V. In an undirected graph, the degree of the vertex is the number of edges incident on it. Then the paths. The path is a sequence. Path is another concept after adjacency and incidence. So path is a sequence of vertices traversed by following the edges between them. So so here, if we refer to this image, we can travel to from 1 to 2 and 2 to 4. So that becomes a path. So that is what we are referring to in this. So a path is a sequence of vertices traversed by following the edges between them. So a path from a vertex U to another vertex U dash is a sequence of vertices, let's say V0 to Vk, in which U equals to V0 and U dash equals to Vk. And all Vi minus 1 to Vi are in E for I equals to 1 to K. So such a path contains the edge V0, V1 to Vk minus 1 to Vk and has a length of K. So if a path exists from U to U dash is reachable from U. So a path is simple if it has no repeated vertices. Next are the cycles. So as shortly mentioned in the applications of graphs about acyclic and cyclic graphs. So cycle is a path that includes the same vertex two or more times. So uh, a directed uh, a directed path, a directed graph, a path of path is a cycle if one of its edges leaves a vertex and another enters it. And as you can see, the cycle in the directed graph A is a cyclic graph as a 1 to 2, 2 to 4, and 4 to 1 again. So in a directed graph, path forms a cycle if v0 equals to vk and the path contains at least one edge. In an undirected graph, the a path from v0 to vk forms a cycle if v0 equals to vk and no vertices are repeated from v1 to vk. So graphs without cycle are acyclic graphs, and direct directed acyclic graphs are also called as DAG. DAG. Next is connectivity. So an undirected graph is connected if every vertex is reachable from each other by following some path. So although an undirected graph may not be connected, it still may contain certain sections that are connected, called connected components. And if the same thing is true for the directed graph, we can say that the graph is strongly connected. That is, every vertex being reachable from each other following some path. And if that statement is true for a directed graph, we can say that the graph is strongly connected. If only parts of the directed graph are strongly connected, the parts are strongly connected components. You can see that the in the image that we have strongly connected components 1 and 4, which are connecting 1, 2, 3, and 4, 5, 6. And it's a directed graph, as you can see. Then certain vertices have a special significance in keeping a graph or connected components connected. So here we will see in terms of an undirected graph. So so any edge whose removal disconnects a graph is called a bridge, and a connected graph with no articulation point is bi-connected. Okay, sorry, I just missed out the point on articulation point. So articulation point is uh, if removing a vertex disconnects a graph or component, the vertex is called an articulation point. So here we have the articulation point of 4 and 5. So in the undirected graph, so if we remove any of the component 4 or 5, the graph will be disconnected from each other. And but if there is a if there are no articulation points, it means that it is the graph is bi-connected, which means there is one way or another to reach it. So although a graph may be bi-connected, its state may not contain bi-connected components. Next is adjacency list representation. So a way to represent it's a way to represent graph, and its structure contains a vertex and a list of vertices adjacent to the vertex. So let's say we have a graph G, where V is the set of vertex and E is a pair of edges. So vertex V is included in the adjacency list of vertex U when vertex. So vertex u and v are forming an edge, and vertex v will be included in the adjacency list of vertex u. So thus, for a directed graph, the total number of vertices in all the adjacency list is the same as the total number of edges. And in an undirected graph, because as you remember that the edge u and v and edge v and u are bidirectional, the number of it will be doubled. So the total number of vertices in an adjacency list, in this case, in terms of undirected graph, will be twice the total number of edges. So you can see the graphical representation of adjacency list. The graphs being represented as an adjacency list. So they are adjacency lists are also used for are mainly used for sparse graphs. That is the graph in which the number of edges is less than the number of vertices squared. And for whenever the graph is dense, we use adjacency matrix representation, which needs the space big of VE. So for the bit of explanation on the image, you can see that one is the first one, and we and we start with it. So you can see that it has the arrows pointing towards 4 and 3. So that's how they are connected. And next is for 2, it is connected to 1. Then 3 is connected to 2, 4 is to 5, 5 is to 6, and 6 is to 4. Then let's start with search methods. Search methods are the way to discover the graphs or traverse the vertices or nodes. So two important search methods for graphs are breadth first search and depth first search. These are important search methods, on based on these methods, many important algorithms are also formed. So both of these work for the undirected graphs also. The breadth first search first explores a graph by visiting all the vertices adjacent to a vertex before exploring the graph further. So breadth first search is used in a number of applications, including finding minimum spanning trees and shortest paths. So we'll see an example of breadth first search first. So whenever we are so the way the images and are going to be represented the vertices, and as you can see in the image 1, the first one is the from the vertex 1 we will be starting. So that is the reason we'll color it gray. And when we have explored its adjacent vertices, which is 2 and 3, so you can vertices adjacent to 1, which are 2 and 3, so those two will be colored gray, and the ones that are white are undiscovered vertices. And whenever we are done with the vertex, we will be coloring it black. So you starting from image 1, as we are starting with 1, we'll color it gray and explore the vertices connected to it, which are 2 and 3. As we have discovered this and we have done with the 2, we'll enqueue in 2 and 3 into the queue, as you can see in the image 2, and color the vertex 2 and 3 gray. 4 and 5 are still undiscovered. Then we'll start with 2, and we'll discover 4. 3 has already been discovered though, so so there is no color change in that. So only color change in image 3 will be for 4. We'll enqueue 3 and 4. Then after exploring the vertices adjacent to 2, we'll move towards 3. So 3, as 4 was already discovered, and there is only 4 to enqueue it, and not any new vertex to be discovered. Then moving to image 5, we go for 4, as 4 does not have any connected ones to it, so its queue will remain empty, and every connections to 4 has been discovered, so we'll mark it black. So now going towards the depth first search. Explores a it explores a graph by first visiting undiscovered vertices adjacent to the vertex most recently discovered, and the search continues, tries to explore as deep as it can. So it keeps on exploring the vertices, and once it has done, it will backtrack to the one where we started. So the use of depth first search is used for cycle detection and topology sorting. Then we can record for the further uses, we can record the times at which each vertex is discovered and finished. Depth first search can also be used to produce a depth first forest. So as you can see, we are starting at 1. So 1 is marked as gray, and other vertices are still white, which means that they are not discovered. Then after discovering 1, 2, and 3, we are keep in mind that we are also marking the edge which are connecting or used for discovering are also marked as gray. So 2 has been discovered, and 3, and we are finishing with 3. Then after backtracking from 3 to 2, then discovering and finishing the 5. So you can see we started with 1, then we discovered 2, 3, and while backtracking we also discovered through to 5, as all the connections for 2, 3, and 5 has been discovered, and we are done with it. We'll go back to 1 and we'll finish 1, and we'll start for 4 again, and we'll discover and finish it. So as you can see that this process of starting from 1, and we discovered each and every vertex, this has to be repeated for each and every vertex, else we have discovered 1, 2, 3, and 5 here only. But if we are not repeating this process for each and every vertex, then we'll leave the vertex 4 undiscovered. So that is the reason we have to repeat this process or steps again for each and every vertex. So that's how we'll discover 4 in the end. So yeah, this is all for the graphs, and which contain theoretical explanations and steps to work with graphs. So I hope it was good, and yeah, thanks for listening. Thank you.
Hey, Jamie, thanks for the explanations. And Shrikant, you have anything since you joined and probably midway? Okay. I think Shrikant dropped out, looks like,
Yeah.
since we have finished. That's okay. So what I'll do is just wanted to make sure that what do you use for implementation of graphs? What kind of structures and interfaces? Any comment on that? Just
So, this session was only divided for. So there are two sessions. This
oh,
one takes care of the theory one, and
okay,
the other one will be taking care of the implementations of it, starting
okay,
with different basic operations that graphs work with.
okay. So this is the graph theory and
Yeah,
graph practice some coding, something you will explain in the next
yeah,
session.
yeah,
Okay, that's so that means I thought this was the last session. I forgot about it. So there is one more session of
yeah,
seven, one more section of
yeah,
session, which will be next one, and there we'll cover the interfaces, data structure interfaces, and coding, and
yeah,
the analysis of the uh, implementation. I think that's good enough, and I think we should sign off. I'll stop the recording now and hope
sure.
to complete the next session soon.